Ok, grazie a tutti di essere venuti e della pazienza di aspettare questa mezz'ora. I'm going to talk in English, otherwise John is not understanding what I'm saying. It's a pleasure to introduce Professor John Axelsson from the University of Stockholm and Karolinska Institute. John is a great scientist, also a good friend. So I'm really happy to have it here and to introduce it to you. John is a psychologist. He's graduated in psychology at Stockholm University as a PhD in psychology. Since 2011, he's a senior lecturer and independent research group leader at the Department of Clinical Neuroscience at the Karolinska Institute. And is also a professor in experimental sleep research, which I really envy you, John, on this, at the Stress Research Institute at Stockholm University. As I told you before, is a very well-known and recognized scientist in sleep research. He has given more than 50 international scientific speaking presentations and more than 300 lectures for companies and other organizations outside academia. Good. And is an impressive ability to be funded for his research. Total funding for the group the last 5 years, more than 2,400,000 euros. Wow. It's a lot. And also envy you on this. He has more than 130 scientific publications, 41 as H-index on Scopus, more than 5,000 citations, and is studying sleep consequences for health and behavior since more than 20 years. Central theme of his research has been to explore how insufficient sleep and inflammation not only alters our physiology, but also our cognition, because he's a psychologist, as I told you, and behavior. So his work is included the development of a human experimental sickness model with injections with endotoxins, and pioneering work on how both sleep loss and sickness drives behavioral changes, and how this in turn affects other people, including sickness avoidance. So this is a very interesting field, and I think John will talk a little bit about it in the next days, not today. Another of his research theme is how sleep loss can make us more vulnerable to other stressors, and why there are so large individual differences in vulnerability to sleep loss. This is part of the talk of today, yes. John and his group are presently carrying out several large-scale studies, including experimental sleep loss in 500 subjects to characterize phenotypic differences in vulnerability to sleep loss and low-grade inflammation. John's research has received a large press coverage. His results have been highlighted in more than 800 media outlets, including scientific journals such as Science and Nature, and 13 of his publications are in the top 1% of all scientific articles with the highest attention. So it's a real pleasure to give the floor to John, and finally, with a long delay, we'll hear about sleep cognition and vulnerability to sleep loss. Thank you.
Thank you very much, Michele, for the very nice introduction. You should never applaud him beforehand. You should wait until afterwards. That's my suggestion. We create some expectations, but I hope it's going to be good. Thank you very much for inviting me, and it's a pleasure to be here. We will see. I will probably skip a few slides, and you have to be sorry and bear with me. But please raise your hand if there's something you don't follow, because I tend to speak a bit fast, and some of you may not be great in English, which I appreciate because we're in Italy. So please raise your hand and ask me a question or tell me to slow down. I'm perfectly fine with that. So with that, I want to start. And before we start, I would like you to think a little bit, what of your weaknesses do you have? Think a little bit about how are you affected by sleep loss or when you're stressed, and consider what are your strengths and your weaknesses, because we're going to talk about it and probably going to predict how you are affected by sleep loss to some degree. And I'm going to come back to that. So what can you expect to hear about today? You can expect us to hear about, I'm very shortly going to talk about what sleep does for the brain. I'm sure some of you have heard it already, but it's always good with a little bit of repetition, and I will probably say it in a different way than other people do it as well. And then I'm going to talk about tired brains in general. How do they function cognitively? How do they change? And I'm also going to talk about why are we so differently affected by sleep loss, probably after the break, I hope. We're going to have a little bit short break, although you started a bit late, and we can maybe have a very short break. And then in the end, I'm going to talk about some new work we're doing more, where I propose a model to explain why we're so differently affected by sleep loss, and also how sleep loss then drives mental health problems in a number of different disorders, because sleep problems is the #1 symptom in psychiatry. It's basically across all psychiatric problems and mental health, and it's likely to be a big part of driving symptoms. We know that it increases the risk for it, but it's also likely to drive symptoms. And I want you to have a little bit of a better thinking of how we approach this and what we're doing in this field. And it also explains some of the effects. I will tell you a little bit about that. Very, very briefly, I am going to talk about how the brain is regulated. So the brain, we need to put the entire body to sleep at the same time. And then we need to have a system to do that. And that system is largely regulated from the thalamus and the brainstem and the hypothalamus. And in the thalamus, we have this is like a relay station, which many consider it of a relay station, but some of these these relay neurons can have a different state. They can either be relay neurons, or they can be neurons that actually wants to put the brain to sleep. They can be oscillating neurons. So actually, if we cut off the brain here, below it, to switch off these arousal systems, the brain, these thalamus neurons or these relay neurons will actually try to put the brain to sleep automatically. So the brain, if you don't have an arousal system, if you switch off the arousal system, the brain will probably automatically go into sleep in many individuals. So that means to keep your brain awake the entire time, you need to have an arousal system that gives some input. And what is it that assures this? Because you have these different nuclei in the brainstem, and we need the system also to make sure that they're active all the time to some degree, and that is called the hypocretin system. So in the hypothalamus, we have systems that either make sure that these systems are active all the time to some degree, and we also have neurons that also inhibit them to allow us to fall asleep. So we have a switch here in the hypothalamus that either tries to keep the brain awake, it's the hypocretin systems, and you all heard of the narcoleptic patients, for example, because when we check their brains afterwards, they've lost about 90 to 100% of the neurons, of these hypocretin neurons, and then you have an unstable system, and then you have these falling asleep occurrences that can happen. And why am I telling you this? One of these important aspects is that to have the brain awake, you actually need to have arousal, some degree of arousal. And also for your brain to fall asleep, you need to switch off your arousal system to some degree. So when you switch off your arousal, it takes some time for these relay neurons to actually hyperpolarize. And when they do that, they can then start oscillate, and then they try to put the rest of the brain asleep. It sends out oscillating signals, and then if there is a need outside in the brain, they will then respond, and there will be a thalamocortical loop when the brain falls asleep. And it means that it takes some time for this to happen in the brain, because you need to switch off the arousal systems. These neurons need to hyperpolarize, and they need to start oscillating, and there needs to be a pressure within the brain as well to respond, so you have to create the thalamocortical loop. And there's a problem for some people to initiate this, because if you have too much arousal, there's a problem to do this, of course. And this is the general theory within insomnia, is a hyperarousal theory, that you have problems to switching off these arousal systems. Yes, because worries and anxieties that are driven, that activates this arousal system, makes it hard to fall asleep. So people who can fall asleep quickly are those who can switch off the arousal systems, and those who have problems will take longer time to fall asleep, and that is related to insomnia problems, for example. So that is a good basis to have in the background when you think about hyperarousal as a main theory of driving insomnia problems. But the brain, that means that I was just explaining that we have a general system that we have a system because we want the entire body to fall asleep. But the need of sleep is not, of course, on the general level. The need actually happens on the local level. It's the cells that need to sleep. That means that when you're awake, there's a buildup of sleep within the cells in the brain, particularly. And then there's some fantastic studies, and this was already 30 years ago, it was suggested that actually the sleep is actually for the neurons and the neural communities, that they will actually fall asleep. So if you take out neurons from the brain, small parts of the brain, they will actually start sleeping, even though in small dishes and so on. So they have sleep-like behavior. And these are some studies, very nice studies, where they had people in the evening, where they did special talks. This is actually a brain, where you have a nose, you have ears, and then all of these dots are electrodes. So this is high-density EEG. And what these people have been doing in the evening, they've been doing specific tasks that activates the left arm. And this means that these areas have been used during this task particularly. And that means that this area that has been more used for several hours means also create a larger sleep need. So that means that this part of the brain that you used more will have more deep sleep the following night, which means that deep sleep is driven by what happened locally in the brain. So those areas you use during the day, they will have a larger deep need for sleep. And this group then created a very nice and genius study that came out later. What can we do to reduce the use of the brain in some part of the brain? How do we make someone stop using a part of the brain for one day? And then they actually used arm immobilization. They put the arm in plastic for the entire day. So that happens if you break your arm or have a plastic arm, and then they made sure that they couldn't use their fingers and hands for one day. And that means that they actually use this part of the brain that is connected to your left arm. And that means that you don't need so much sleep in that part of the brain the following night. And this shows that your buildup of sleep need happens in the cells throughout the brain. And it actually, the deep sleep then represents the usage of these areas. And that means that activity during the wake time drive the aspects for slow wave sleep. So what does then sleep do for the brain? And these are some things you've heard of, I'm sure, before, but there are a few new things that also are quite interesting. So what is really known is like the homeostasis. You need to retain homeostasis to recover from what happened during the day. And one of these new findings, which that we clear waste products, and this was shown basically 10 years ago by Michael Nerdegaard, who's a Danish researcher and also in America. And basically what happens in the brain, it's protected by the brain barrier, and we didn't really know how the brain clear these waste products that actually build up. So there are toxins and waste products, and when the brain is really, really active, it means that there's a lot of waste products. It's also a lot of proteins that breaks down and that are misfolded, and that we need to take care of. And we have to take care of them either by cleaning them away with a flushing system, like the lymphatic system in the body. We have a lymphatic system here, but this is what they explain. Other way is that the glia cells have to eat them up, actually. So that means that that is much more problematic for the brain if they have to involve the immune system or the glia cells of the brain to do this, because it causes inflammations, and then it relates to problems in the long run with small inflammations in the brain. And what they showed here is that the flow here is during wake time, the flow is really, really superficial, close to the blood-brain barrier, but the flow is goes much deeper into the brain and much more efficient, this clearance within the brain when it's during sleep. And they show actually that the effectivity of the cleaning system was up to 2,000% more effective during the sleeping period. So that is one of the very, very hot areas. And there are now actually new studies in humans as well, showing that the clearance of their cerebrospinal fluid is actually also more effective during the sleep period. It's actually to some degree seems to be driven by the sleep itself. So that's quite exciting work that's happening in that field. There's also a lot of cell repair of the brain, and most of the work that exists here is that, particularly in the DNA, and there's some really nice new studies showing that if you have more breakdown of the DNA, that means that these animals will then sleep more the following night and support these processes. So the DNA repairment seems to be more problematic. It doesn't function so efficiently during wake time, and when they have more DNA destruction, that means that you are better at repairing them during the following night. All in animal studies, of course. And there's also important aspects that we talk about sleep and energy homeostasis. So there has been long proposed for a long time, and work that actually that because we use so much energy during the brain that we need sleep to fill up with these kind of glycogen stores or ATP stores during the night. It's a little bit problematic to make the conclusions that it is the case. There seems to be so, but it's also that we use much less energy during the night. So it might be a natural aspect. But there seems to be quite important that for the brain to function properly, having the good brain energy homeostasis is quite good to sleep for it. And there's some really, really new exciting work, particularly for synapses. Because you know that neurons are quite stable in the brain. There are a few areas where we have new neurons. But the synapses change dramatically every day. Most of our synapses actually change every day. And that means that we need to fill them up because they do so much work. They have to function all day, and they also need to be plastic for the next day. And during sleep, they fill up with these proteins that they need to use. You've heard of dopamine or serotonin or noradrenaline and GABA and glutamate and all of these transmitters that they use, they also need to function. So they fill up vesicles with these proteins. And also the receptors need to be functioning. So that means that for synapses to be able to function a full day, they need a full night of sleep to fill up. So there's a lot of work now on these protein changes and happening within these synapses. And that could be one of the main reasons for sleep. I believe in that is one of the major factors, that synapses are something that is extremely plastic and changes in the brain. And there seems that sleep seems to be very, very important for these synapses to function properly. So that is restoring. And then, of course, also sleep does also work a lot with plasticity and adaptive changes. And this is what Michele Ferrara and Federico and the people work. And they work a lot with these memory changes. And then there are some really classical studies where, from the 90s, where they show that the hippocampus is involved in declarative memories, as you know, as psychology students. But hippocampus then is involved in the connectivity to different parts of the brain where processing this information. And during wake time, this is of course stimulated by the outside world, and hippocampus's role here. But when we then during sleep switch off the outside world, there is a replay here, and this replay is then orchestrated by hippocampus. The original idea is that actually there's a consolidation where these memories are moved from hippocampus out to the different parts of the brain. This is now sharp wave ripples. But some more new ideas actually question that a little bit, that it's actually, the memories already exist out here, but you need to replay during the sleep, and that seems like hippocampus is then the orchestrates that activates the same pattern as before. Rather than transferring the memories, it's actually just reactivated. This is hippocampus important to keep memory of which areas are involved in the order they do it, so they can make a replay what's happened during the day. So that's actually, you don't only experience everything during the day, you also re-experience things during the night, and hippocampus is now coordinating this reactivation during the night. And that means that when you've had the experience, you have like a re-experience during sleep, and that means that these memories are more consolidated during the next waking period. There's also a lot of work on synaptic homeostasis. So if you have a system that actually learns everything today, that means that you tag them, the neurons become larger, and that means you need to also have a system that reduces the size of these synapses. Because if you learn and have a system that all the synapses become stronger with usage all the time, you need to have a system that also removes the synapses that are not active all the time, and remove those synapses from the system that you don't want there. And that actually seems one of the hypotheses from Giulio Tononi that you might have heard of, is that the purpose of sleep is to remove those synapses. And actually during sleep, that during the wake time, so what they did here is that they measured actually the size of synapses throughout several parts of the brain in animals. And then they showed that at the end of the waking period, your synapses are bigger in general. And at the end of the sleeping period, they were then in average 18% smaller. And that's a huge difference on average. And they showed that that means that during the sleep period, most synapses become weaker. Not all of them. There were 20% of the synapses were protected from being removed or weakened. But it does show that we have a system that every day is synapses that increase in size because of the usage. And also during the night, most synapses are then reduced. And that means that you have a system that all the time that adapts to your environment. And those synapses that you use often in your environment, because that's activating them, will be protected. But those synapses, they're related to things in your brain that doesn't happen, or you don't reactivate, and they will be weaker and weaker and removed from the system across time. So sleep is basically the price for plasticity in this aspect. There's also some recent findings, or which actually Freud already proposed a long time ago, that sleep is important for emotional functioning, and that dreams are related for your emotional function. And there are a lot of work now suggesting that this is true, and basically that you have that amygdala is a hub in the brain that is activated when you have emotions. It's like a survival circuit to some degree, and you have these reactivations during sleep. And the idea is that when you experience something for the first time, you have a strong amygdala response. You get affected, and the idea is for a functional system is actually then to be slightly less affected the next time. You shouldn't be as afraid or as angry when you experience something again. And the idea is that actually this reactivation or changes or functional change that you don't have to react as strongly happens during REM sleep to a large degree. And what they did show here is that they made people sing karaoke. Have you sung karaoke in here? You sing good? So what they did here is that actually they removed your own songs. You couldn't hear your own voice, and then we made people singing karaoke, and then they replayed it to people, and then people got really embarrassed, and this is the embarrassment you feel. So you get an amygdala response where you're embarrassed and have to listen to your own song. Most of us, at least. I would be very embarrassed if I listened to my own song. But the idea is that you don't have to react as strongly the next time you listen to this. And that means that the day after, so they related then, they made people listen to their own songs, and then this is the response they had. And then they did it the next day, and then they predicted how good they were going to be, or how it's going to reduce their activity, and how much less they're going to be reactivated the next day by the amount of REM sleep. And the more REM sleep, the less they then reactivated. And they also had the connection. So it's both the duration of REM sleep, but also more even the disturbances of REM sleep. And the theory say that you need undisturbed REM sleep to downregulate your emotional system. And this goes in line with some work where during REM sleep, there is a slight reduction of noradrenaline. So during the day, you have noradrenaline flowing, which is very important for your arousal in the system and keeping focus and other aspects. But having this replay of these emotional memories, when you actually reduce noradrenaline, allows the system to remove the stressor, so you don't have to react as strongly. And this is some really nice, exciting work that Michele and Federico here are doing, and other people in the group here, that you can actually, by helping people or disturbing the REM sleep, can actually make people then be less emotionally reactive. And this is actually based on some studies already more than 20 years ago, showing that people with PTSD, they follow people that have experiences, and they show that people who had more disturbed REM sleep were more likely to develop PTSD. So there's a lot of work actually relating this to anxiety and PTSD conditions. So a tentative summary so far: homeostasis, sleep refreshes the brain through many restorative processes and optimize so you can actually function a full day in the next day. For the adaptivity, sleep supports plastic changes, so you're more plastic, the hippocampus works. For consolidation, it fine-tunes network, it actually replays things, and it proves functioning by simulations. I see the brain as a simulation machine. It's quite good to then think that the brain continues simulations also during the sleep period, but then you can then fine-tune the system, you can incorporate things, and you can make systems more functional for the next time. And the idea for the brain is to assure a fully functioning brain when you're awake, and it's actually to allow the entire system to sleep allows us to have a fully functioning brain when you're awake, because otherwise you would have parts that would falling asleep all the time, indifferently of each other. So that's why we synchronize it. You have a general sleep system. And this is important because if people don't have enough sleep, or when we force them to have work night shifts, for example, long periods, then you will have parts of the brain that has been used more, and they will be more tired. So the main function, I would say, of sleep is to allow the entire function of the body to be fully functional when you're awake, and you don't have systems that need to sleep. You make sleep, now everything needs to sleep. I mean, I have twin children, I had twin daughters when they were small. Rather than them having separate lives, I made them sleep at the same time, we made them eat at the same time, so I could then have a life. Otherwise, to have two separate systems, that wouldn't work. So that's the same I see sleep. You synchronize the system, so everything does the same thing. Everything sleeps at the same time, and then you have a fully functioning system when you're awake. So then we go into tired brains. How can you think about tired brains? And if you look into the meta-analysis of the cognitive consequences, I'm focusing on cognitive consequences today. And then you can see simple attention, you have strong effects. And these are analyses of studies where you don't have any sleep at all for the night. You also have effects on working memory and more complex attention, quite strong effects. You do seem to influence process speed and short-term sleep, or short-term memory aspects, but a little bit weaker. And if you look to reason accuracy and more high cognitive functions, you don't find much effects. There are slight changes, but they're often not significant. And that means that the brain is actually quite robust against the consequences of sleep loss. But you are vulnerable when we need to keep up attention. Attention is it's very valuable for the brain. It's actually what are we going to focus on? And focusing on something that the brain doesn't like to focus on, that has a little value, doesn't give any dopamine, is problematic for the brain. And you really have to use your executive functions to keep up the control of something. And that is particularly vulnerable to focus on something that is particularly boring, for example, for a long time. And working memory to some degree. So these are the main effects. And there are other studies, like on sleep restriction studies, meta-analysis that shows the same thing. So this is quite stable, that attention is the number one aspect, and then working memory, and then you have these other processes and higher cognitive function, to a large degree quite actually resilient to sleep loss. So if you look into a meta-analysis on brain studies, and then you can see what are the kind of brain areas or connectivity networks that are affected. And this is when they do attention tasks, of course, so it's a little bit related to that. But you do see there's a reduction in blood flow, in activity, in those areas that's involved in the frontoparietal attention network. So basically, to keep up your attention, you need to involve both areas in the parietal lobe and in the frontal lobe, and those are affected. You have a reduced activity in those areas after sleep loss. You also have a reduced activity in the salience network, and that is insula and medial prefrontal cortex. And what is in the salience network? The salience network is involved in everything you do. It gives a value of things, how important things are for the brain. So it's important because the salience system helps the brain give focus and attention. What is important for me? It gives a value on things. So everything is really, really important in helping you guide your attention and focus and have working memory on what is important, for example. And the insula is one of these important hubs for regulating the salience network. And dopamine system is involved in the salience network, for example. And these studies also show an increased activity in thalamus. Whether this is related to them being sleep in a thalamus activating, I'm not sure, because if you do fMRI studies, have you done an fMRI study here, any one of you? Well, if you've been in the scanner, it's extremely noisy, and this recurring noise, and it's really hard. I always fall asleep when I go into an fMRI scanner. So if you have people sleep deprived, put them in the scanner, I'm sure many of them fall asleep. And then you also get an activation in thalamus. You start actually wanting to put the brain to fall asleep. It's really a bit hard. I believe it's an effect of people actually falling asleep in the scanner, but I'm sure it could also be that you already have more activation and flow in thalamus to actually initiate sleep in these people that are really tired. So if you look into these, number one aspect of cognitive functions, harder to keep up attention. Sustained attention, particularly most attention. So boring, sustained attention across long time is problematic. And what are the components that drive this? There is one homeostatic component, meaning that the longer you're awake, the worse you will become. And the other one, there's a circadian component, meaning that it's more problematic to perform at the middle of the night and in the morning for most people. And if you follow people who've been kept awake here for 60 hours, you can see that they're all getting worse across time, but it comes in a circadian fashion. So actually during the day, during 16 hours that most of are awake, they do perfectly fine. And these are actually how many lapses they have during these attention tasks. And then you can see during the first night, there's a steep. And then here at the bottom of 5, 6, 7, 8 in the morning, people are worse. And then they actually get better again during the next day. And then the next night, they get much, much worse again. So the performance is not only the sleep consequences of being awake, this homeostatic pressure, but it's also a circadian component that actually helps you perform much better than you otherwise would in the middle of the day, and much worse than you otherwise would only from the homeostatic point of view because of the circadian phase. So if you try to perform at 5 or 6 in the morning, it's really, really hard. And that's basically what. So the deterioration across time is influenced by these aspects. And of course, if you fall asleep, then you can, or have a nap or something, then you can counteract some of these consequences. So if you increase sleep loss and sustained attention, this is the typical way of people getting worse. It's not that they get the general slowing, because that's what is reaction time. On average, people get worse, but using average is completely wrong, because people are actually, this is how they perform after 12 hours. This is one subject, an example. Many of them look like this. They have quite stable. These are the reaction time tests over 10 minutes. You see they're a little bit slower a few times, but the longer people then kept awake, 36 hours here, but particularly then 60 hours, you can see that what happens is that the brain actually have a lot. It functions as normal most of the time. If you look across here, it actually functions more than half of the time. It functions quite well, but it has period where it completely misses, and it has these lapses. So the brain does not only become slower, it particularly becomes stochastic. It actually fails to perform completely. So it has this kind of instability or increased variability. You can think of the brain as becoming more variable or more unstable after sleep loss. And the people are a little bit slower in general, but that's very, very small effects. So the big thing is that people become more variable, and you can think of the brain as being more unstable with increased sleep loss. If you look into sleep deprivation and attention, and then compare it to working memory effects, and then you can see that this is a study by Lowe and colleagues with Derek and Dake's group. And then when you sleep deprive people and they perform at the night, you can see the largest effects overall is, of course, people become more sleepy. That beats every other effect we find. Sleepiness is the main factor if you sleep deprive people. You get worse in attention, and you also have different NBAC tasks of working memory here. So easy working memory tasks are not so affected, but more complex working memory tasks like a 3 NBAC, then you get more affected. So working memory is affected, but much less than attention aspects, for example. And we did similar studies, and we find very similar effects of total sleep deprivation. So attention gets worse, mainly. Sleepiness worse. You also get worse on math, episodic memory, and working memory, but the effects here are much smaller than if you look into attention, for example. But you have a number of these consequences of sleep loss. You also get worse at learning. I'm not going to talk much about learning, because you have people in the group here that are much more experts on learning than I am. But there are some classic studies showing that when you make people do declarative memory tasks, you activate hippocampus. It's a reduced activity in hippocampus, and people are worse at learning, which means that for your brain to be able to encode during the day and learn things, like here, for example, to remember things from what we talked about today, you need the hippocampus to function. If you haven't slept well, and this is a study where people didn't allow to sleep at all, you have a much reduced activity in the hippocampus, but also other studies showing that even a slight reduction of slow wave sleep have similar effects. So you need your sleep to have a hippocampus to be able to be plastic and functioning the next day properly. You also have a reduced connectivity in the brain, and that means that when you activate and do different things, you have connectivity patterns in the brain. Depending on what you do, you switch these connectivity patterns. And you need to sleep properly to be able to actually keep up these connectivity patterns. And one consequence is these connectivity you have become more unstable, and that also means that your ability for your frontal lobe to control functions are reduced. So this is one of them is emotion regulation. So there's a number of studies. I will just show examples. Is that yes, you have a reduced connectivity, particularly from the frontal cortex to other parts of the brain after sleep loss, and particularly to regions that are both in cognitive control but also in emotional control aspects. And you also, this kind of reduction in connectivity seems to be related also to more to activity of sleep actually in the brain, like theta activity locally more in the frontal lobe. So the brain frontal lobes connectivity loss is also that might be that you actually have intrusions of theta activity here in the frontal lobe. This is a classic study done by Matthew Walker's group with the sleep-deprived people, and you can see amygdala activity here. And they were exposed to these kind of IAPS pictures, if I remember correctly, that activate amygdala to see horrible pictures. But you can see that amygdala in your emotional response is much, much stronger if you haven't slept properly. And they connect that to reduced connectivity, because normally when we activate our amygdala, we always can regulate it with our medial prefrontal cortex. That's one of the functions of the frontal brain, is actually to be able to regulate your emotions and other aspects. And what they see after sleep loss is that you have a disconnect here. So the connectivity is reduced and disturbed during after sleep loss. And that is many other studies. And I would also say there are some studies that have not found this, but Most studies have found this, but there is still some kind of controversies in this field. So how important are naps? Do you take naps? So people sleep all over in Sweden, that's why I always talk about this, because Sweden and Scandinavia, we remove naps earliest in the world. 2-3-year-olds, we think like maybe they shouldn't have naps so they can fall asleep easy early in the evening, so the parents can have some time on their own. They're a bit selfish, the parents there. But of course, children and people take naps and siestas all over the world, and we don't in Sweden. So this is a fantastic study. This is one of my favorite studies. It's not a very big study, but they removed the naps in children that were 3, 4, 5-year-old, and they wanted to see what happened. And what they did, they could then make puzzles. So they could either make a puzzle that worked, and they also could do a puzzle that didn't work. They actually had an impossible task in front of them. And then they filmed them, and then they let other people then rate what happened, how these children reacted when they made these puzzles. And these are the children. This is in the nap, after they've been napping, and this is after when they didn't remove the nap. And then you can see how happy they were when they solved the tasks, with the puzzles. You can see people, not all children, this is one child in each condition, so each line here is a child. Not everyone was happy by solving, but most children were happy solving the puzzle. And then you can see, in general, many of them were much sadder when they were not so reactive, were not so positive when they solved this task. But even more important, because we face problems all the time, and these children then had this impossible task. And then you can see how negative they were, and then you can see when they've had a nap, they were not so negative. Some of them were negative, they didn't like it, which is not so surprising when you have problems. But most of them were much more negative. Basically, I think there's one child that didn't change, but all the other ones were much more negative when they didn't get this puzzle to work. And even more important, that's negativity that they had. And this is actually, how are you supposed to react when you have a problem? You need to stay up, you have to be confused and curious and how to solve this problem. And then you can see, not all of the children were confused or curious, in the nap condition. Some were not so interested, but most of them were. But after the no nap, no one was curious or confused in trying to solve the problem. So what happened in these children, when they remove the nap, when they face a problem, they get more negative and remove their ability to learn. They don't want to solve the problem. They don't care about the problem. They only get negative, and they don't get curious or confused or trying to solve this problem that they have at hand. So you actually have a change in their behavior and remove their capabilities. So giving children a nap allows them to actually have 2 learning periods across a day. One, you learn during the morning, you have a nap, and then you still can then recover, and if it's long enough, you can actually have reconsolidation of memories, and then you can actually have a secondary learning period in the afternoon and evening. So that's one of the areas I'm talking about in Sweden, to try to let people have the children to have naps. If they fall asleep, they need the sleep. That's not more problematic than that. It's a good solution is more naps to many problems. So, Michele, I'm not sure, shall we have a little break? Or I go on for 5 minutes, because one aspect I wanted to mention, I'm not going to talk a little bit more about actually next week, is motivation, but I'm just going to very briefly say that sleepiness is a motivational state. We have completely misunderstood sleepiness in the field of sleep loss and consider this the probability to fall asleep. But sleepiness is a subjective state that wants us to sleep. It tells us to avoid other aspects and to sleep. And the more sleepy you are, the more you want to be home. You want it to be dark. You want it to be quiet. And you want to be lying down. You want to be you want to lie down and you want to sleep. And it's related to shutting your eyes. And the consequence is that you want to avoid other things, which is social and physical and other aspects of activity. So it drives our behavior quite strongly. And I'm going to talk quite a lot more about that because it's important for many aspects. And I will also then present that the effects of sleep loss are exactly or very, very similar to those you are when you're sick. So sickness behavior, which is a big thing, you also have a very same response actually by sleep loss behavior, to be honest. I will talk more about that next week. But the purpose of sleepiness is to organize behavior to assure that you have sufficient sleep. And there's always a but in science. And the big but is that we're extremely differently affected by sleep loss. And this is a classical study by Van Dongen's group, and they had people do these boring attention tasks, and they had them 3 times, once after baseline and twice after they hadn't slept at all for 1 night. And then they compared how much worse they were after each of these sleep deprivation as compared to normal. And these are subjects here, and this is how much worse. So if you were better, you would be below here, but no one is better in attention after sleep loss. You don't get better on anything after sleep loss in attention, at least. And then you can see how much worse you are. And if you did a study, and they concluded how much worse you're after sleep loss, you say, yes, you get worse attention. And if you did a study on these, maybe 20 people or 19 people, you would make the conclusion that people are about 50 to 60% worse, or lapses here. But that is only true for about 1/3 of these people, because 1/3 is much more affected. They're getting much, much more affected. And then you have 1/3 that is hardly affected. And these are, of course, the people you want to be your bus driver or your pilot driver, because they're not going to fall asleep. Because even a 1 night day of full sleep loss, they still have no problems to keep up attention on something boring for a long time. So these are the ones who are really tolerant, and these are the ones who are really vulnerable. And these are the ones that are the average. And then you can see the interesting is that people react more or less exactly. So this is the 2 different times. They react extremely. So this person was really strongly affected the first time, and exactly the same the second time. Exactly. The only person that is a little bit confusing, this person is reacted here and there, but I'm sure that this person should be here, but then they gave up the next time. It's extremely boring to do this task, I can tell you, and then they didn't give it next time. So then I think that person should be here instead, but just gave up at this time point. But otherwise, you can see people react extremely. That means that we have a very strong trait in how we are affected by sleep loss, and it's very, very different. But everyone gets worse after attention. But here you can see that it's also when you read reports in science that people say this is how you're affected, but it might only be true for a few subjects. And some subjects are much more affected, which effects actually drive many of these studies, that you have some subjects are really vulnerable, and then you have some that are actually quite tolerant. And they did the same for subjective sleepiness, and then you see you react very similar in subjective sleepiness. But interesting here is that this person here, for example, who gets most sleepy, difference in sleepiness, is actually it's only here in the middle of attention. So that means that we are differently aware, we have different responses. One is attention capacity, and other aspects are differently affected by sleep loss. That means that we have the consequences of sleep loss is that we have different vulnerabilities. Some people react with more attention problems. Some people will be more subjectively affected by it, for example. So with that, I want to suggest we have a little break. Because we started really late, and I'm probably going to have problems, I'm going to remove a few slides for the second talk. But please come back. Is it okay to like 6-7 minutes or something like that? Try to do that. Okay, 10 minutes. But try it to be a little bit shorter, because then it takes 10 minutes. Perfect. Thank you. So I have been asked, so yes, I will provide the PDFs. So if anyone wants to see the slides afterwards, that's no problems. Michaela will organize something. If you want to see the slides, that's perfectly fine. I will make them available for you in some way. So if you look into these very large individual differences, this is a little bit, well, sorry if I lose my track sometime, but I will try to keep to it. So of these individual differences, you can estimate, if you look into the effects of sleep loss and you compare it, so a very large part of the variance is related to individual differences. So typically when you do these studies, they can estimate that between 70 and 90% of the variance that they find is related to individual differences, which means that when we make conclusions about groups, we will miss the big differences that are related to individual differences, that some are much, much more vulnerable and some are much more tolerant. So why are individuals so different? So what is known of the mechanisms is generally related to genetic makeup. So what kind of polymorphisms you have. And they're particularly in the sleep-wake regulatory systems or arousal systems. I will give a few examples. But there's a lack of other models. So that's something I will propose soon a little bit. And if this is not so easy to get a picture of, but if you look into these kind of genes that we've been looking into in the history, what makes you what kind of genes is it that predicts how you're going to be affected by sleep loss? So then you can see that there are those related to sleep regulation. There are some that are regulated, particularly related to BDNF, is like plasticity. And then the other ones that have the main aspect are those who are related to the arousal system. So if you look into the adenosine receptors aspects, which adenosine is a byproduct in the system that inhibits activity. And if you look into the dopamine sensitivity, and then you have those receptors are relate to dopamine. How sensitive are you to dopamine, and how the COMT gene is actually related to the inactivation or downgrading of for these dopamine, noradrenaline, and epinephrine. So that means that this system that is part of regulating your arousal in the brain, differences between individuals, is related to how vulnerable you are to sleep loss. And there are also some of these that also seem to be part of the immune system. So this has been shown so far. And the research showed that quite large effect in these small studies. So they're definitely involved. And if you look into the arousal regulation, you can actually this is a very short recap of what most of you already know. I mean, you have the cholinergic system and the serotonin system from the brainstem pons area here. You also have the noradrenaline system and the histamine system, and they've all been kind of part of the activating of the ARA system, of the ascending reticular activation system, and the histamine here from the tuberomiliary nucleus. And that means that you have this traditional arousal system. What has been now more recent years is that dopamine system is also very much regulated in wake regulation and keeping up attention and helping us. And of course, dopamine is part of also many disorders. And when we, for example, treat people with ADHD, we give them stimulants, and then we actually activate the dopamine and the cholinergic system, mainly with these kind of stimulants. And also then the hypocretin system that I talked about. So that means that we have many arousal systems that helps regulate how the brain functions during the day. And we manipulate them when we try to help people. So in psychiatry, people often, most of these drugs actually stimulate these arousal systems to a large degree. And if you look, so my question for you, when you sleep deprive someone, what do you think happens? How are these systems affected when you sleep deprive someone? Will them be less activated, or will they be more activated? Any question is good here, because I was wrong once upon a time. Mine and my hypotheses are wrong. If they were all correct, I shouldn't be a scientist, because I'm not brave enough then, and then they're doing things. So what happens is when you sleep deprive people, they compensate by activating these systems more. So that is the way we do all the time. When we stress something or we use a system, we activate the system, and that happens also with sleep loss. So if you sleep deprive someone, they will release more dopamine. You increase the tonus of dopamine in the system. And what do you think is the consequence then of having increased levels for some time? What do you think happened with the receptor systems? Yeah, correct. So that is one of the consequences with sleep loss, is there's a down regulation and a lower affinity in the binding of these receptors. So sleep loss is important for the tonus in these systems, but when we sleep deprive people, they can compensate. They do it perfectly fine. The problem is that across time, and you do it more strongly, then there is a down regulation and of the receptors. They become fewer receptors, and they also have a lower affinity, possibility to round. So one of these classic studies in mice and rats have been showing that if you sleep deprive them, then actually after a week of sleep loss or reduced sleep loss, they have much fewer receptors for serotonin. And we try to manipulate the serotonin system to treat depression, for example. So sleep is really important for these systems to function properly. And the example where we actually know most is in the dopamine system. And there's an upregulation of dopamine, of the tonus of dopamine after sleep loss. And the problem is that is also then there's a reduced availability of receptors. Already the next day, of some of these receptors are reduced, and there's an increase of metabolites in the system. And then because there are more dopamine metabolites, because they're generally inhibiting, you can then now create a system that is not so flexible. You use the system compensate, but of course it's a consequence of doing that. You have a system that is a little bit less functional. It becomes more unstable and more variable when you do this. And increasing the aspect, so you have a reduced availability on D2 and D3 receptor. An increasing aspect is that coffee doesn't only go to the adenosine system, it actually increases the amount of dopamine receptors as well, these receptors. And one aspect is that if you change the dopamine system, the tonus of it, that means that things become less interesting for you, because the difference in the dopamine system is actually the difference from the dopamine kicks. So that actually is a regular part why the dopamine, this tonus, changes your motivation when you sleep deprived. So that is one example of the dopamine system. This is a classical study where they put EEG on train drivers. And they did this already in the 80s. And then they saw if there were intrusions of sleep. And this is during daytime. And intrusions of sleep, here is the EEG continuously during the drive. This is in minutes from 0 to 4 hours, 240 minutes. And then you can see actually this is the wake brain, your normal activity over 16 hertz in the beta activity band. And then you can see that when people fall asleep, they start having activation here, of course, in the alpha activity, theta activity, and then they have deep sleep. They have slower. This looks like a slower sleep, but this is an artifact, of course. And what they did is that they also did this during the night in this train driver. And then you can see in the beginning of the ride, and then there's a quite long, it's 300 minutes, means it's 5-hour ride during the night. You can see there's an intrusion here, particularly in the alpha band. So the longer the ride is, the more alpha this person has during sleep. But it's not only alpha. You can also see at the end of the drive, you have activation of in the theta band, and also actually to some degree the delta activity. And then you can see in this person driving, this person actually have intrusions of sleep during the drive. And this person misses actually the red light, and this is a train driver, and this is a real train driver driving. And this is what happens. People are, of course, more problematic. And when they put the EEG on people who work during the night, 20 to 30% fall asleep during the night shift. This person did not fall asleep because they're standing up, train drivers, so they don't typically fall asleep. But they can fall asleep, and this happens. And this is general sleep, so you don't know what part of the brain, but it seems like there are probably local areas of the brain. And there are a number of classical studies that show that the brain doesn't need to fall asleep completely. You can actually have areas in the brain that falls asleep. Those areas that you use have an increased need. I showed you that in the beginning, that you have more deep sleep in those areas you use, but that means that the build-up during the day becomes larger across the day. And if you don't allow the brain to sleep, then those areas will actually decide to fall asleep anyway. So small circuits of cells will have an increased sleep need. They can actually sleep while the rest of the brain is awake. And this is some ingenious studies where they actually made people do different things, and they did this for many hours. I think they did it for 2 hours at a time, and they did it for, I think it was up to 8 times. So it's been many hours doing the same thing. So they actually activated the same areas. And one time they listened to an audiobook, and they activated the frontal areas more. And then the other time they played car games when they much more activate the parietal lobe. And then they checked, I think they were awake for 30 hours, so they were awake for some time, and then they could then stably see that, yes, here you had more sleep while they were still awake in these frontal parts when they had activated them, and here it's more in the parietal parts, meaning that the local sleep you have is dependent on the areas you've been using. So those areas you use create an increased need in that local area, and if you're not allowed to sleep over time, that area will actually fall asleep anyway. And this is, of course, they maximize this by making people doing exactly the same thing for a long time, but it will happen to you as well if you do something. And that's always what we've done told to shift workers, switch working tasks, otherwise you can't stay awake during the night. So it's good to switch tasks, because then you activate other areas that doesn't have the same demand for sleep. So where you're going to have your local sleep depends on the areas you've been using. So there's a buildup of fatigue or need, and that is, of course, more likely to fall asleep in those neurons or group of neurons. And there's also been studies then in humans with intracranial EEG that's been showing this, and there's also studies in car driving, tired travel, and they can then see that before people drive off the road, you can actually have local sleep in those premotor and motor cortex areas. And that predicts that there's a buildup of theta activity in those areas involved in the premotor cortex before they actually drive off the road, for example. This is in simulators, so this is not in real life. So yes, we have local sleep, and it depends on, of course, sleep loss, but also the usage in those areas. So if you want to have a thinking of how a sleep-deprived brain looks like, functions, it's a brain that wants to save energy and sleep. That's what the brain wants to do. It becomes sleepy, it becomes lazy, it doesn't want to do things, it becomes a bit worse mood, particularly reduce the positive moods. You become less plastic, so those areas involved in plasticity are less plastic, but you're actually quite good at compensating. We activate compensatory systems, arousal system. There are some signs, not so many studies, that you activate more areas of the brain when you sleep deprived, so you can compensate. Like you do when you put in effort normally, you activate more areas as well. You can have local sleep in neural assemblies that have been using. There are some suggestions that it also involved in these high maintenance zones. And that means that you will have loss of specific functions. You can also have a more unstable connectivity for the brain. It's hard for the brain to keep up connectivity for long time periods. And you create a state that is like wake state instability. So rather than being bad all the time, if the entire brain functions perfectly fine, you might not remember as much, that's less plastic, but it can do things quite well. And then it will have periods where it doesn't stop functioning, depending on the connectivity loss or the sleep loss. And that means that when we have doing non-time dependent things, like not attention or working aspects where you have to be on time, where you have this kind of fast dependent, you can actually compensate by thinking more and doing things. And that's why we probably don't find effects on you do higher cognitive functions where you can put more effort and time into things. So when there's no time constraint or no attention aspects that can directly influence it, these kind of local aspects, we're quite good at compensating. Although we are, of course, it's harder for us, and the brain doesn't want to do these things. So if you want to look into sleep loss and instability, yes, it's good to be physically active and socially active, and it's kind of a good loop because they both drive sleep. So more social activity and more physical activity actually drives sleep. And the other way around, sleep well, you have more energy, and so that's the functioning. If you don't sleep or have problems sleeping, the number one aspect, you become sleep and you want to sleep more. That's the number one aspect. And the number one cognitive aspect, you reduce your attention task. You've been more easily distracted by other things, for example, if you have that aspect. So you also get more moody, you get less positive particularly. You have an increased risk for accidents and risks, so that is the acute aspect. I'm not talking about health consequences that develop over time, but the number one is that you have problems with accidents in the car aspect. So if you have sleep problems, don't drive the next day. If you're going to have a long drive, make sure you sleep. In Sweden, we have a law 6 hours. In Israel, they just made a law or rule in their military. Everyone that has to drive the next day, they need to sleep 7 hours. There's a 7-hour minimum sleep for military personnel so they can function better. So this is like to ensure you have a fully functioning brain for accidents. You get worse memory encoding after sleep loss. You also get worse emotional regulation. There are some aspects of aggression, the relationship between aggression, that people are more aggressive the days after a bad sleep. And you also become more pain sensitive. But now I say you become, but that's not true, because most of you will have worse attention, not all of you. Some of you will be more moody, and you react differently. You have different vulnerabilities to sleep loss, and that's why I asked about what are your weaknesses. That means that your trait weaknesses will predict how you're affected by sleep loss. We react differently. You don't say that everyone gets worse memory after sleep loss, everyone gets worse pain. No, that's not true. Some of us are. So when you hear about the consequences on media or TV, they say you get worse by sleep loss, you get cancer by sleep loss. No, you don't get cancer by sleep loss, full stop. There's not very small few data on that, but other risks like cardiovascular disease, there's a risk for it, but there's of course the risk increase is 20-30%, which is quite large, but it's still only a few people that's going to be affected by it. So we don't react at all in a similar manner to sleep loss. We react very differently. So think about that. We're not all getting worse after sleep loss. Another thing I want to highlight now at the last part is that sleep is a transdiagnostic symptom. I told you it's the most common symptom within psychiatry and mental health problems. And it's a primary symptom. So the symptoms in some of these disorders are also very similar to sleep loss. We have fatigue, which is a common problem. That's what you get sleepy and fatigued after sleep loss, which is also common in many disorders and mental health problems. Attentional problems, emotional instability problems, worse mood. And that means that sleep loss can drive these consequences, and these disorders drive these consequences. And that means that there's a mix-up. When is what causing what? And the idea here is that sleep disturbance is extremely common in these disorders. So you look into mental health problems, particularly between 50 and 95% of these populations have sleep problems. And that means that there could be a good idea to actually look into sleep problems in many other disorders. Is the Microsoft, can we? I have it on here. I hope you can hear me online. But one of them needs to be on. One of them, both would be problematic, I guess. But this one is on. No problems. So that means that what is causing what here? We don't know, but what we can think about it is that if you have sleep problems, the days you sleep worse, then these symptoms, of course, will also be worse in these disorders. That means that sleep loss problems is not only increasing the risk, it will also drive symptomatology and problems in a number of different disorders, but it depends a little bit of what characterizes the disorder, of course. So let's see. So we need models to help us understand this, and we have the genetic models, but we here propose a different model, which I'm going to go through a little bit. And this model is called based on the research domain criteria, which you might not have heard about. But it's a nice model that NIH, or NIMH, which is basically the Health Institute, National Institute for Mental Health in America, they proposed this in 2009, and then they decided you are not allowed to look into groups as patients unhealthy any longer, because that's not going to help us understand the mechanism behind problems. And the idea is that you look into strengths and weaknesses of the natural variation of a number of different traits within the population. And that will much more better expect. So the idea for our aim is to identify these kind of traits that predicts why people are phenotypically, characteristically, why they're differently affected of these different vulnerabilities. So I will very briefly, for those who don't know the research domain criteria, it's a very nice proposal actually. It's the framework is to investigate mental health problems, and the goal is not to solve everything, but to get a better understanding of the mechanism and the diagnosis and prevention, because diagnosis is very different from country to country. It depends not on the underlying traits, it depends on the problem and symptomatology and the context people are in much degree. So it's much better if you want to understand mental health, we need to look into the mechanisms instead, and this is a way to do it. And to understand the varying degree of dysfunction, I'm actually reading now because I can't say it better myself. Several basic dimensions will better explain the full range of human behavior from normal to abnormal. So everyone can be classified into these kind of dimensions. And that means that if you classify yourself in different cognitive aspects or in psychiatric traits, that will probably help you understand where your weaknesses are and what problems you have when you're stressed and when you're sleep deprived. So that is our basic background that we used, and that means that I just did an example of some of these traits. For example, ADHD trait. So here is attentional problem traits, which is a central part. There are several traits in ADHD, and that means that some of this is how we are looking at the population. Most of us are here in the middle. Some have no problems with attention at all, and some have more varied attention, more instability or inability in attention. And some of them will have ADHD diagnosis, but the diagnosis is not related to this, it's related to the dysfunction in different contexts where they need help. That's why people put the diagnosis. And that means in some contexts, very few get ADHD. In some countries have it. In some contexts, like in school, where you institutionalize our kids, of course, more are going to have problems. And in the States, there are certain areas where 20% of young boys have an ADHD diagnosis in the States. In Sweden now, 11% of young boys have an ADHD diagnosis because school is not an ideal place, a context. They have dysfunction when you have these more attentional problems. So that means that these kind of underlying traits explain the underlying problem, and then the diagnosis depends a large part of the context. And what we believe is that sleep loss and stress will make more people problematic in their attention problems. So these are much more vulnerable than others, but we also believe that people that are on this side are also going to be vulnerable to sleep loss or other stressors. And then we can look into different aspects. We look into autism field, for example, as well. So there you can look into this dimensional aspect that these are vulnerable people. It doesn't mean that they have a diagnosis, but they're likely to have a diagnosis if they don't have the right support, if they're not intelligent enough to find good strategies, if they don't have help to find strategies, they're even more likely to need medical help or other diagnosis. So I will present a few data from a study that we've done. So we took 182 people, we randomized them to normal sleep or total sleep loss, and then we wanted to see if ADHD predicted vulnerability, and we predicted specific vulnerabilities of their symptoms at central cognitive aspects that's central for the disorder, or the ADHD trait disorder. We don't have patients here actually, although some of them should be straight traits. We also took a group with psychosis. Is the underlying degree of psychosis predicting perceptual instability, which is their problem? Psychosis is related to perceptual. They have a different world than the rest of us. We all are psychotic to some degree, but because we don't have problems, we don't get the psychotic disorder or the diagnosis. Our worlds are not different enough for us to get the diagnosis. And then we also have the intelligence, whether intelligence actually predict tolerance to sleep loss. That was our idea in that paper. But I'm going to discuss that in this afternoon. And then just to show that in this group, yeah, we have nice distribution of attention and emotion instability. And if you look at cutoff here, some people are at risk or should be evaluated for diagnosis, like in the entire population. So this is a population sample. We don't find a healthy group or something. We took basically everyone, and then you see we have this natural variation of people. And some probably should have diagnosis, and some might have as well. And then we predicted that people with inattention traits, they would have more inattentional problems. And people with emotional instability traits, they would have more emotional instability problems. And we also predicted that the problems were going to be variability in the system, which we talked about, that the brain is sleepy, it's more variable. It's not slower in general or more inaccurate, but it's more variable. And we also believe, because these are also shown in this ADHD, that people are generally more variable. So their problems is also variability, so which is the same as sleep loss. And this is exactly what we found. So in the group that slept, having high on the inattention traits did not predict worse conflict or instability in this conflict processing. This is a Stroop task with conflict instability, and this is an emotional Stroop task. And then we can see in the groups who didn't sleep, you can see those who are higher on the scale with more inattention problem traits, they are the ones vulnerable. And the same for the emotional instability conflict. Higher in instability traits are those who are affected by sleep loss. And this tells us many things. It tells us that if these people sleep well, they don't have problems. It also tells us that these people are higher on the scale. They get more problems when they sleep too little. So sleep loss is a way to reduce resources for these people. But it's also interesting that people are low on these traits. They're not affected. So if you did a study on people and excluded sick people, you wouldn't find any effect at all on these consequences. So that means that vulnerabilities and different cognitive functions are driven by vulnerable individuals. Now we have 180 people, but we need even more. So we're doing a study of 500 now, because it's probably that these effects are probably not linear. It's probably driven by smaller groups that are higher on these scales. So yes, we do show quite clearly, and attention is one of the aspects that's particularly vulnerable to sleep loss, but we do show that people are very differently vulnerable. There are people that in attention traits, they have certain problems. People with emotional instability traits, they have certain problems. And the problems is not a general worsening, it's a more variable brain in those cognitive processes, in this processing. So yes, ADHD domains predict vulnerability to sleep loss in those particular domains that they measure in the trait aspects. And that means that when you have a trait, it doesn't mean that you are like that all the time. It means that you're state vulnerable in general. You can think of it, if you have high on these ADHD traits, which at least 20% in this room should be to some degree, that means that you probably do quite fine. My colleague, so he's a professor, he always makes sure to sleep 8 hours because he say he can't function properly the next day because he has too much ADHD. So we can find strategies to counteract these vulnerabilities that we have. And one of them that he doesn't drink too much, and he never sleeps less than 8 hours, for example. So that's one way to counteract these vulnerabilities. We did another study on psychosis proneness to see if psychosis predicts So we measured the trait of psychosis with the Peters delusion inventories based on how delusional are. We are all delusional to some degree, but some people are more delusional than others. And there's this particular test called the perceptual stability, and it's a quite weird test because it's just dots on the screen and they're flickering, and you often believe that they actually go in one direction, but they don't. But the brain, this is an illusion, interprets it to go in a certain direction, and this is a quite stable illusion. That either you predict it go to the left or you predict it go to the right. That's how we are. And then sometimes they switch this, but most of the time it goes in the same direction. And people who are schizophrenic, they have a reduced stability in the system, so they more often switch in their data. So people who are schizophrenic, this is a typical test that actually measures schizophrenia or perceptual instability, because people switch more often in this illusion, because it's an unstable illusion that you have. So we do say, what happened after sleep loss? Yes, so people are really stable. They stay in the same kind of choice. They do a new choice every 10 seconds. They stay much more, but after sleep loss, people stay much less. That means that become more unstable in their psychosis, in their belief, or in their illusion here, actually. We did not find an effect of psychosis. It did not predict here. So yeah, our model did not work. It was against our hypothesis. But we do show here that then, so people have slept, they're stable across the entire trial. And then, of course, when you start after sleep deprivation, they're also stable in the beginning, and they get more and more worse across time. So they're more unstable or unstable in their illusion here at the end of the period. So that's typically what you see in studies, that they're degrading in that. And also that if people have had a lapse or failed to respond, then they're much more likely. That means that if you have an attentional lapse, you reset the system, and then you become a little bit unstable in your illusion or interpreting this kind of this task. So, but the problem is that we found that even though we had 180 people, we didn't have so many people. So that means that psychosis, people have even a different degree of psychosis, but you actually need more psychosis on these scales to actually find more problems. So we probably had a too healthy group in this case to find effects. That could be one of the consequences. But yes, perceptual systems become unstable with sleep loss. We did not find any evidence for trait in this case to drive it. The other aspects I'm not actually going to present because we're going to quit soon, but the intelligence was our idea that intelligence protects against cognitive consequences of sleep loss. And as you can see, yeah, intelligence is related to better cognitive performance in episodic memory, and particularly when you have to use your brain, like in arithmetic and ability mathematical tasks, you're much faster and more correct. And the idea is how are you affected by sleep loss? But I'm not going to tell it because we're going to discuss this paper this afternoon. So we will come back to that after that. So tentative conclusions on this RDoC approach. ADHD predicts specific vulnerabilities to sleep loss in those different domains of ADHD. Psychosis proneness did not in this case, but using this RDoC approach of looking into dimensional approaches in different traits that we have is likely to predict vulnerabilities to many stressors, not only sleep loss, but sleep loss is one way to reduce our ability to compensate. That's how we can see it. But there, of course, we will also be more likely to be influenced by stress in those systems as well. Although there are different stressors, you have weaknesses, and you have weaknesses that are probably driven by different kind of stressors. So what I suggest for everyone to know is to learn in your own traits, your cognitive profiles, your psychiatric profiles, to know your own weaknesses, and then understand why, when you have problems in these, you can actually see if it's sleep loss or other stressors that drive your weaknesses, or your mental health symptoms, or cognitive weaknesses. And then you can actually find strategies against them when you have a better understanding of your profiles or your weaknesses profiles. So take-home messages. Sleep serves multiple restorative functions for the brain. If you look into the cognitive aspects, I'm not looking emotional or motivational and behavior. Tired brains are less attentive, they are less plastic, and they're more variable in their functioning. We are differently affected by sleep loss, very, very differently, and consequences are most likely to be related to your weaknesses that you have, and those traits will predict them. And also that vulnerability to sleep loss are also likely to drive problems in a number of mental health problems, where you have the similar symptoms, which fatigue, attention, mood, emotional processing problems are involved in. With that, I want to say thank you. And that was on time, actually.
We have time for questions if you have one or two. And then we go to lunch.
But don't say that. You have a question. I will also be here this afternoon, so we can have more questions at that time as well. But we're going to discuss 2 papers, the Journal Club, and I hope you've read at least 1 or 2 of them, and we're going to have a discussion about them and discussion about these aspects. I'm happy with that. So the question is for everyone, also online, is what this model has an advantage compared to the previous models of genetics. Of course, we can do genetics to see, but we have so far only looked into single polymorphism, and that's not how traits look. So we know that each trait is related to many, many, many genetic aspects. So this model will give a lot of different scattered information, while the model we propose is based on your behavior or the expression of behaviors or underlying functions in a number of different aspects that we all know very easily where we are. We know our BMI. We can very scale know our inattentional problems on an inattention scale. So it's a much easier model to understand people, because the genetic models, they're of course going to help us, but they're very, very young. They can only explain certain behaviors of very, very common polymorphisms, because it's really hard to study uncommon polymorphisms. And we can, if you have large-scale studies, we can much more detailed find out these vulnerable groups. And it's much more easy than having separate studies. But we are going to actually, because we are doing a study now with 500 people, we can replicate all previous genetic studies and show if they're wrong or right, because we have much better power than they have, because they're typically 30 people or 20 people or 10 people or 15 people in each group. And we have 500 people with those more polymorphisms and other polymorphisms. We can tell them if they're true or not. And the large-scale studies with these, we can much more tell how many are tolerant, how many are vulnerable on different functions, which is genetic studies cannot do. They can say some group is more affected, but we can then more estimate the true effect sizes. We can then estimate how many are vulnerable and how many are tolerant, and how many are a little bit affected, for example. So rather than saying that sleep loss having a significant effect, that's not very useful. Is it clinically relevant or not? That's the idea. That is where we need to go. Are these effects clinically relevant or relevant for your everyday life? And then we can say we have 30% who are really affected. It's probably clinically relevant for them. 70% probably not. So that's what we want to make conclusions about. And I think our model is much better than genetic models in that aspect. But I might be wrong. I'm often wrong. Thanks everyone online.